All right, so today we're diving into something that's pretty crucial in AI right now, the whole idea of interpretability. It's one thing to have these powerful neural networks doing all sorts of amazing things, but if we can't actually understand why they're making the decisions they are, that can be a bit of a problem.
Yeah, especially as we're seeing deep learning being used in more and more, sensitive areas, right? Like in medicine, for instance, or even in criminal justice places where you absolutely need to be able to trust the system's judgment. It's not enough to just get a prediction. You need to know what led to it.
Exactly. So that's where this whole field of explainable AI, XAI, comes in. And the paper we're looking at today dives into a pretty interesting approach for XAI using something called concept activation vectors, or CAVs for short. Have you worked with these much?
Oh, yeah. CAVs are a really cool way to try and connect what's happening inside a neural network to, concepts that we humans can actually understand.
I mean, you've got these complex mathematical spaces inside these networks, right? So how do you even begin to bridge that gap to something like, say, recognizing a cat in an image?
Well, that's the beauty of CAVs. The basic idea is to represent a concept like cat, in this case, as a specific direction within that complex internal space of the networks. Think of it like an arrow pointing towards catness.
So like the more the network's internal activity aligns with that cat direction, the more confident it is that it's actually seeing a cat.
Precisely.
Right.
And the way they usually train these CAVs is by essentially showing the network a bunch of examples that clearly have the concept. So lots of pictures of cats and a bunch that don't. And the system then tries to figure out the best direction, that arrow that separates those two groups of examples based on the network's internal response.
Okay, I'm starting to get the picture, but the paper we're discussing today highlights a bit of a snag with this whole CAV approach, something they call concept entanglement.
Ah, yes. This is where things get really interesting. So you can imagine that in the real world, certain concepts tend to appear together a lot, right?
Like if you see a picture of a beach, you're probably also going to see, water and maybe some palm trees, right?
Exactly. And what happens is that when a neural network learns from this kind of data, it can end up kind of mixing those frequently co-occurring concepts together in its internal representations.
So instead of learning a separate beach, water, and palm tree direction, it sort of smooshes them all together into one big entangled mess.
Well, not quite a mess, but yeah, the lines between those concepts can get blurred. So when it sees a beach, it might automatically activate all those related concepts, even if only one of them is actually present in the image.
Okay, so why is that a problem? I mean, is it really that big a deal if it gets a little confused about what exactly it's seeing?
Well, it can be, especially when you start thinking about applications where you want to very specifically understand or even manipulate how the network is processing individual concepts.
Oh, I see. So like if you were using these CAVs to, say, edit an image and you wanted to just add, a hat to a person's head, but the hat concept is entangled with, say, sunglasses, you might accidentally give them sunglasses too, even if you didn't want to.
Exactly. It's like trying to adjust one slider in a photo editor and having a bunch of other unrelated things change at the same time. Not very precise.
So this paper tackles this whole concept entanglement issue head on. And what's particularly interesting is that they're proposing what's called a Post-Hoc method for disentangling these concepts. So they're not trying to prevent the entanglement from happening in the first place. They're trying to fix it after the network has already learned.
Right. Which is actually quite practical because in a lot of real-world scenarios, you might be working with a pre-trained network that you don't necessarily want to retrain from scratch.
Okay, so can you walk us through how this post-hoc disentanglement magic actually works?
Sure. So the key idea is to encourage the CAVs for different concepts to become more independent of each other, to point in more distinct directions within the network's internal space. And they do this by introducing something called a non-orthogonality loss.
Orthogonality, like in geometry where lines are at right angles to each other.
Yeah, exactly. Think of it this way. If two CAVs are perfectly orthogonal, it means they're completely independent. There's no overlap or confusion between them.
So their goal is to basically nudge those CAV arrows so that they're pointing in more perpendicular directions.
Precisely. And the clever part is that they're trying to do this without messing up how well each CAV actually represents its intended concept. They want to separate the concepts without losing their meaning.
That makes sense.
Wow.
But how do they actually measure this non-orthogonality? I mean, it's not like they have little protractors inside the neural network.
Right. They use a mathematical trick called cosine similarity. It's basically a way to measure how much two vectors, or in our case, CAVs, are pointing in the same general direction. A cosine similarity of 1 means they're perfectly aligned. A cosine similarity of 0 means they're orthogonal.
Got it. So the more similar the directions of two CAVs, the higher their cosine similarity and the more entangled they are.
Exactly. And what they do is they calculate these cosine similarities between all possible pairs of CAVs and put them all into a matrix. Then they compare this matrix to what's called an identity matrix, which is basically the ideal scenario where every CAV is completely independent of every other CAV.
So the identity matrix is like the orthogonality goal they're aiming for.
You got it. And the non-orthogonality loss is a measure of how far away the actual CAV cosine similarity matrix is from this ideal identity matrix.
Okay, so they're basically quantifying how much entanglement there is. Now, how do they actually use this loss to disentangle things?
Well, they add it to the original loss function that's used to train the CAVs in the first place. So the overall training process is now trying to balance two things: making sure each CAV accurately represents its concept, and making sure that all the CAVs are as orthogonal as possible.
It's like trying to hit two targets at once, right?
Yeah.
You need to make sure each CAV is both accurate and independent.
Exactly. And there's a weighting factor, which they call alpha, that controls how much emphasis they put on each of those two goals. A higher alpha means they push harder for orthogonality, but it could also potentially hurt the individual CAV accuracy if it's pushed too far.
Makes sense. Now, they also mentioned this idea of targeted orthogonalization. What's that all about?
So sometimes you might have a situation where only certain pairs of concepts are really strongly entangled, like
Right.
maybe beach and water are super entangled, but palm trees are pretty distinct.
So instead of trying to disentangle everything equally, they can focus their efforts on the specific pairs that need it most.
Precisely. It's a way to be more efficient and avoid potentially messing up CAVs that are already doing a good job on their own.
Smart. Now, one thing that really impressed me about this paper was that they didn't just focus on the math. They actually ran some really interesting experiments to show that this whole disentanglement thing actually works in practice.
Yeah, they used both real-world and synthetic data sets, which is a good way to test the robustness of the method.
For the real-world data, they used this CelebA data set, a bunch of images of celebrities with all sorts of different attributes labeled like hair color, wearing glasses, smiling, that kind of thing.
And for the synthetic data, they created a really cool data set called Funny Birds, where they could precisely control which bird features appeared together, like beak shape and tail feathers. It's like a concept entanglement playground.
Yeah. So what did they actually find? Did their method actually work?
Oh yeah, it definitely did. They showed that by applying this non-orthogonality loss, they could significantly increase the orthogonality of the CAVs, sometimes even achieving near perfect orthogonality.
And importantly, they also checked to make sure that this disentanglement didn't mess up the ability of each individual CAV to represent its concept accurately.
Right. They used a metric called macro-averaged EROC, which basically tells you how well a CAV can separate the concept-present examples from the concept-absent examples.
Yep.
And they found that in most cases, the ROC either stayed the same or even improved after disentanglement.
So not only did they separate the concepts, but they actually might have even made some of them more accurate in the process.
Exactly. And they also found that the weighting parameter, alpha, played a big role. Higher alpha led to better orthogonality, but if it was set too high, it could start to hurt the AROC. So there's definitely a sweet spot there.
Makes sense. Now, to really get a visual sense of what was happening, they also used this technique called layer-wise relevance propagation, or LRP, to create heat maps. Have you used those before?
Oh yeah, LRP is a great way to see which parts of an input image are most important for a particular concept, according to the CAV.
So what did the heat maps show after they disentangled the CAVs?
Well, they showed that the heat maps became much cleaner and more focused on the actual concept. There was less of this spillover activation in areas that were associated with correlated but absent concepts.
So it's like before disentanglement, the network might have been looking at, say, a person's whole face to decide if they're wearing a hat. But after disentanglement, it focused more specifically on the head area.
Exactly. The network's attention became more precise and less influenced by these spurious correlations.
That's pretty amazing. But the real proof is in the pudding, right? Did this disentanglement actually lead to better performance in real applications?
That's the key question, isn't it? And to answer that, they explored two very relevant applications of CAVs. One called concept insertion and the other shortcut suppression.
Okay, so what's concept insertion?
Imagine you want to take an image and add a specific concept to it, like giving someone a beard. You can actually use CAVs to guide this process by nudging the network's internal activations in the beard direction.
So it's like using the CAV as a sort of concept steering wheel.
Exactly. But as you might imagine, if the beard CAV is entangled with other concepts, you might end up with some unwanted side effects.
Right. Like you might accidentally give them a mustache and a goatee too, even though you just wanted a beard.
Exactly. And what they found was that by using their disentangled CAVs, they could insert concepts much more precisely without those unwanted additions. The network was able to isolate the desired concept and manipulate it independently.
That's a really powerful demonstration. So what about this shortcut suppression thing? What's that all about?
So sometimes neural networks learn to make predictions based on kind of superficial correlations in the data. These are called shortcuts. For example, imagine a network is trying to classify images of cows and sheep.
Okay.
And let's say that in the training data, all the cow images happen to have green grass in the background, while the sheep images have brown dirt.
All right. I see where you're going with this.
The network might learn to simply look for the color of the background to make its decision, instead of actually focusing on the features of the animals themselves. That's a shortcut.
And that's bad because if it encounters a cow on a dirt background, it might misclassify it as a sheep.
Exactly. So shortcut suppression is all about trying to get rid of these spurious correlations so the network learns to rely on the true underlying features. And what the researchers found was that their disentangled CAVs were much more effective at suppressing shortcuts with less collateral damage compared to the original entangled CAVs.
Collateral damage. What does that mean in this context?
It means that when they tried to suppress the shortcut, they didn't accidentally also mess up the network's ability to recognize other unrelated concepts. The disentangled CAVs allowed for a much more targeted and precise intervention.
Okay, so to sum it all up, this paper presents a really promising technique for untangling the way neural networks understand concepts. And they've shown that this disentanglement can not only improve our ability to interpret these models, but can also lead to better performance in real-world applications.
Yeah, it's a really nice contribution to the field of XAI. And it opens up a lot of exciting possibilities for future research.
Which brings us to our novel notions segment.
Yeah.
Where we like to brainstorm some, well, potentially crazy ideas inspired by the paper we just discussed.
All right, let's get those creative juices flowing. So one thought I had was, what if we could take this whole disentanglement thing and make it dynamic?
Dynamic, you mean like changing over time?
Exactly.
Yeah.
So the current method uses a fixed level of orthogonality, meaning it pushes for the same amount of separation between concepts throughout the entire training process.
Right.
But what if we could make that level of orthogonality adjust based on, say, the specific input data the network is processing or the particular task it's trying to do?
So like if it's looking at an image of a formal event where beard and necktie are highly likely to appear together, it could crank up the orthogonality between those two concepts. But if it's looking at, I don't know, a nature scene, it could relax the orthogonality a bit.
Exactly. It's like the network could become more context aware and adjust its level of concept disentanglement accordingly.
That's a really cool idea. How do you think that could be implemented in practice?
Well, it might involve incorporating some kind of attention mechanism that can dynamically assess the level of potential entanglement in the current context and adjust the weighting of the orthogonality loss accordingly.
So it's like giving the network a little knob to control how much separation pressure it applies to each pair of concepts.
Precisely. And I think this could have some really interesting implications for not just interpretability, but also for things like fairness in AI systems. If certain sensitive attributes are often correlated with non-sensitive ones, you could use dynamic orthogonality to try and disentangle those relationships more effectively during the analysis.
That's a really insightful point. It's like by being more selective about when and how you disentangle concepts, you could potentially mitigate some of the biases that can creep into these models.
Exactly. It's all about being more nuanced and context aware in our approach.
Okay, so dynamic orthogonality, definitely a novel notion worth exploring. Any other ideas brewing?
Well, another thought I had was, what if we went beyond this idea of linear orthogonality? I mean, the cosine similarity measure that they use is a linear metric, but what if the way concepts get entangled in these high-dimensional spaces isn't actually linear?
You're right. Neural networks are notoriously nonlinear. So you're suggesting that maybe we need a more sophisticated way to measure and disentangle these relationships.
Exactly. What if instead of thinking about these CAVs as arrows pointing in different directions, we think about them as representing more complex curved shapes within the network's internal space?
Whoa, that's a pretty mind-bending concept. So instead of just trying to make the arrows more perpendicular, we might need to reshape the entire geometry of those concept spaces.
Precisely. It might involve using techniques like Connell methods, which are good at capturing nonlinear relationships, or even trying to learn a nonlinear transformation within the latent space itself, a mapping that specifically aims to disentangle the concepts in a more complex way.
That's a really fascinating direction for future research. It's like suggesting that we might need to develop a whole new language to even describe how these concepts are intertwined.
It's definitely a challenging area, but I think it has the potential to unlock some really deep insights into the inner workings of these models.
Well, on that note, I think we've reached the end of our deep dive for today. We've explored a really important and innovative technique for making AI more interpretable by disentangling those tricky concept representations. And we've brainstormed some pretty exciting avenues for future research that could take this work even further.
It's been a great discussion, and I think it really highlights the importance of continuing to push the boundaries of XAI so that we can build more transparent, trustworthy, and ultimately more beneficial AI systems.
Couldn't agree more. Thanks for joining us on this journey into the fascinating world of concept disentanglement. As always, we encourage you to check out the original paper, which you can find linked in the show notes, to delve deeper into the technical details. And we'll catch you next time for another exciting deep dive into the latest advances in machine learning research.